Okay, this month we are taking a look at Google's benchmark library for microbenchmarking. And just to be completely honest up front with a disclaimer, I am not any kind of expert in performance benchmarking. This is probably the first time I've done any kind of formal performance benchmarking. So this is just an introduction to how to use this library. It is not meant to be an exhaustive list of best advice on how to make your code run faster. We're going to see some experiments with variations on a single algorithm. So we're going to see some examples of how to provide different implementations, measure them, and identify which ones are better, which ones are worse in terms of performance. Now, in a modern computer, you'll see that there are many variables that go into affect performance, and that makes it challenging to make a library that measures performance because the compiler, the memory subsystem, what else is happening on your machine, background tasks executing in a multitasking operating system, the thing you're trying to measure can get preempted because your chat client decided to wake up and send you a notification. Many different things can interfere with measuring performance, and it's difficult to control all of those. The big difference between when the C language was first created or even when C++ was first created is the access to memory on a modern computer has many different consequences depending on cache systems and so on, and there's a lot of different things that can interfere with you think you're accessing memory and you think it's going to be fast, but it ends up being really slow. So there's many talks on YouTube that go into a lot more detail about the memory subsystem and how to make that better for performance. Most of it involves rearranging the locality of your data so that you get better cache hit performance. So I'm not an expert on all those things. I understand how caches work and I understand how data locality can contribute to better performance, but that's not what we're going to focus on today. What we're going to focus on today is just using this library to get some basic measurements to compare algorithms, and we'll use that to guide our choices going forward as we try to get better performance out of our code. So Google's benchmark library, it's on GitHub, so Google /benchmark on GitHub. And the documentation, there's an overview on their main README page, but there is a user guide that provides detailed information on using the library. The documentation is pretty good. It doesn't take long to read through the whole thing. And it's if you've used a Google test, it's similar in that you write a function that is going to be your benchmark, and then you invoke a macro to call your function. And within your function, there's a benchmark state that is passed to your function, and you use that to control the inner loop that you're trying to measure. Now, what the benchmark library tries to do, and this is one of the challenges of, let me go back here just to get back down to the simplistic example here. You write a function, you invoke this benchmark macro on that function to get a benchmark test case recorded into the system, and the system will pass you in this benchmark state. Typically what you're going to do is write a range for loop over that state and do whatever it is you want to measure inside the body of the range for loop. And the reason that this is structured this way is because what benchmark is going to try and do is run your code. Each test case is going to run it a few little times to try to figure out if your benchmark code runs really quick. We need to run many iterations of it to get a statistically useful measure of what the performance is. If your benchmark test case takes more time to execute, we don't want to run it hundreds of thousands of times. We want to run it just a few times if it takes a long time to run, so that it can use kind of comparable wall clock time to the other test cases, so it'll get fewer iterations if the code takes longer to run. So that's what this state variable that is passed into your benchmark function, that's what it controls. It basically controls how many iterations of the thing you're executing are going to be invoked for the benchmark. You can think of it as a test case. It's like a benchmark case, really, more than a test. I mean, you can turn a benchmark into a test, but a benchmark itself doesn't produce like a pass-fail. It just produces a metric. You know, how many things did I do? How long did it take? So this is the simplest case. This is the case, or the usage that we'll be using, because I don't need to do anything particularly fancy. But when we look into the user guide, as you write more benchmarks, you're going to end up with more things that you want to do in terms of configuring the benchmark, eliminating duplication between benchmark, eliminating variation between benchmarks. And you see, this is the idiom here that they use, that this benchmark macro actually evaluates into a pointer to some configuration state, and then you can take the result of that macro and basically invoke methods on it. It works like a builder pattern where you just keep each one of these methods returns the pointer back, so you can invoke make another method call and another method call and another method call and so on. And here you see in this example, they're saying run the benchmark, and we're going to provide an argument value of 1 and an argument value of 3, and then we're going to try it with 16 threads, and then we're going to try it with 32 threads, and then we've got a setup function that we want you to invoke before the benchmark starts, and we've got a teardown function that we want you to invoke when the benchmark is finished. And because it ends up being a combinatorial, or it ends up being a combination, rather, of the args and the threads in this particular case, you can see in their little table down here, it ends up turning into invoke it with arg1 and 16 threads, invoke it with arg1 and 32 threads, invoke it with arg3 and 16 threads, and then invoke it with arg3 and 32 threads. And the different methods that you can call on this pointer are well documented in their user guide here, and it configures the sets of inputs to the benchmark and the number of threads that go into the benchmark, and how those, do those inputs form like a range of integers, or do they perform a set of integers that aren't just increasing by 1, but they're increasing by 8, or so that 0, 8, 16, or is it multiplied by 8, and so on. So there's a bunch of different ways to configure the range of inputs that are passed into your benchmark. Typical example here, they're benchmarking memcopy. So this is the body of the benchmark. This is the thing that's getting measured, but they're varying the number of bytes in the source and destination as one of the inputs, this arg value. That's one of the inputs to the benchmark itself. So each iteration of the benchmark is using that number to decide to say how many bytes to copy from source to dest, from source to destination. and that you get that from this state variable that is passed into your benchmark function. So all the inputs to your benchmark are packaged up into that state structure, and this range of 0 represents the value that's passed in for the first call to or the first argument to this arg function. Now, and you see down here they're calling the arg function with 8, 64, 512, 4K, and 8K. But there's ways to simplify this down where they're using the range function, the range function instead of the arg function, and there's range multiplier, and so on. There's a lot of different of the versions of these member functions that allow you to specify different input patterns for the benchmark. Now, in my particular case, I didn't avail myself of any of that because I just did a straightforward benchmark. I didn't do a lot of variation in terms of these inputs to my algorithm. So I'm kind of, got fixed inputs to the different benchmark cases, and I'm just running the different cases with different algorithms. So, as I say, this documentation it's pretty long, but it's not terribly long. It's all basically in one page, and basically, in terms of configuring the variation into your benchmarks that you might want to compare against, that is relatively easy to do, including multi-threaded benchmarks where you need to vary the number of threads. You may need to do some kind of one-time setup before any of the threads are executed. There's ways to do that. You may need to do some one-time setup before a benchmark is run. There's ways to do that through a setup function. You can share setup and teardown work between benchmarks by using fixtures. You can add custom data into the report generated for a benchmark with custom counters. We will show an example of that, and we'll show an example of adding information to the context. Now, the context is basically a summary of information about the environment in which the benchmarks were executed, so your CPU type, speed, and so on, all those kinds of things. So when you compare two benchmarks results between two different machines, and one is faster than the other, and you might be wondering why, it could just come down to the context in which the benchmarks were executed. The one machine could have a faster CPU, the other one machine could have a faster memory subsystem, and so on. May have more threads, so that you have a thread parallel algorithm may complete faster on a machine with more threads. Just to give you an idea of what this output looks like, here's the result of the benchmark that I've created as an example. Here's the context up here. This last line down here, static target SSE2, that is a piece of information that I added to the context. That's for a couple of months back. We looked at the Highway library for SIMD programming, and Highway has a static dispatch where you target a particular SIMD instruction set extension based on compiler flags, so it's static because it's chosen at compiler time, and that's this span highway static case. And then there's a dynamic dispatch where it dynamically probes your CPU and picks the what it believes is the most performant instruction set extension and uses that for the implementation. And I tried to figure out how to get the dynamic target name output into the context, and wasn't able to figure out how to do that. For the static context, it's easy, or for the static target, it's easy because it's determined at compile time. So you can call a little function that gives you this string. For the dynamic one, if I called that function to print the target name from inside my dynamically selected implementation, it of course printed out the corresponding name for the implementation that it was executing, but wasn't able to get the right target name printed out from outside the implementation that was selected. So I wasn't able to add that to the context. But for the purposes of just demonstrating this library, this just shows you how to add something to the context. So you can see here, this is the kind of report that you get from this benchmark library. Now the report can be in one of a couple of different formats. Really, there's only two that are useful. There's the console format, which we're looking at here, which it just prints to standard out. And there's a JSON format that is more useful for doing more, metrics analysis over time, comparing, you might have a situation where you run the benchmark on a standard machine configuration against somebody's proposed changes like a pull request, and if the benchmark changes beyond some allowed threshold, then you call it a failure because you made the performance 5% slower, and that's not acceptable, or what have you. And that's most easily done by capturing the results of the benchmark run into JSON, and then using some kind of tools to compare existing performance versus the performance of the pull request. Now each, if we go back here, just go back and look at their top level README. When you call this benchmark macro, now they call in their documentation, all their benchmark cases begin with BM underscore whatever. Whatever is the argument to that benchmark macro is the name that shows up here in this table for the particular benchmark. If I'm writing a benchmark function, I don't feel the need to put benchmark into the name of the function. It's clear from the context that it's a benchmark function, so it's not going to be confused with something else. So I didn't use any magic BM prefix or anything like that. That's not required by the library. That was just the style that they chose to use inside their documentation. And you see here, there's a time column. This is wall clock time. So this is the amount of time elapsed for invoking all the iterations that were invoked for this benchmark. And then there's the CPU time, which can differ because if while executing their benchmark, the operating system decided to suspend your process, that won't count against the time that your process was suspended, won't count against the CPU time that was taken to execute the benchmark, but it will count against the wall clock time. And you'll see here that this iterations column is the number of iterations that it executed the inner body of your benchmark. So in that range for loop where you're looping over the contents of the state, even if you don't care about like the, any kind of parameters like that as our access to that range accessor on the state structure, you're still going to execute your code inside some kind of loop. So this is the number of iterations that the loop was executed. And then this user counter over here, this total iters, this is a value that I'm reporting, and we'll see what that looks like in a second. So let's go look at some code. So how do you get benchmark? Well, the easiest way is to use, I think, is use VcPkg in manifest mode and just specify that you want benchmark along with any other dependencies that you might have. The benchmark, it's, in VcPkg, excuse me, in VcPkg, any library that you depend on, if it has direct dependencies, VcPkg will go and get those. But in your manifest, you list whatever your direct dependencies are. So I'm depending on benchmark for the microbenchmarking facility. I'm using gtest to just unit test some code that I wrote for this example. And I'm using that highway SIMD programming library to explore some different algorithms. Now, what is it I'm benchmarking in this code here? What I am doing is go look at my library. I have let's go to this header. So I am benchmarking different approaches to implementing computing the Mandelbrot set. So in this header, these iterate functions, they take a single point in the complex plane and they do the Mandelbrot set iteration on that point up to some maximum number of iterations, in this case at 64K. And they return the number of iterations that were computed to determine if this point designated by a real and imaginary coordinates in the point in the complex plane, to determine if that point was inside the Mandelbrot set or not. So either if it was determined to be outside the Mandelbrot set after a certain number of iterations, and that is the count that is returned, or the maximum iteration count was reached, it was assumed to be inside because we did the maximum number of iterations and it still did not, the orbit of the point did not exit the bounds of the Mandelbrot set, so therefore we could not determine if it was outside, and so it is assumed to be inside. This is pretty standard fractal stuff for computing fractal images. In our case, we just want to compare different implementations. Is it faster to use floats or is it faster to use doubles? Is it faster to use the complex number class from the standard library or to use our own hand-rolled complex number class? Or what if we just dispense with a class abstraction altogether, no value type, we just use raw floats or doubles to compute the orbit of a point to determine if that orbit exceeds it's what's called the bailout criteria to determine if that orbit is inside the Mandelbrot set or not. And another thing that we're going to do is we're going to compute a span of pixels and return a vector of iteration counts, one for each pixel, between a starting point in the complex plane and an ending point in the complex plane, and we're going to take a certain number of samples between the start and the end, the number of pixels, and again, do that with the standard complex class from the standard library or our own homebrew complex class, or just using flat out floats and doubles and doing the complex math by hand instead of letting a value type complex number class do that for us. And then it doesn't really make sense if we go back over here. Let's close that window. We don't need that. If we go back over here to iterate, the reason you don't see any highway code here is that it doesn't really make sense to try and use SIMD algorithms for a single point because each point in the sequence is dependent on the previous point. So there's a data flow constraint that we can only compute the next complex number value from the previous complex number value. So there's no opportunity for parallelism in computing the points in the orbit in parallel because of the data dependency. Each point is dependent on the previous point. So there's no highway variation of the iterate algorithm. But in the algorithm that computes the iteration counts for a span of pixels, we can do that in SIMD. And that's what we did in the presentation on the highway library a few months back. So these are the things we're trying to measure. And in order to do that, we've got a little 3 separate files here in our benchmarking program. Let's take a look at the main function that I've written first. So there is a way to just get the boilerplate main function from benchmark. And, to write this function, I actually cheated a little bit. I just If you look at, let's go back over here to the, you see there's this macro benchmark main. And if I take that macro and put it in my code, let's just turn this off so we're not getting any suggestions from Copilot here just to get in the way. And if I use ReSharper and say expand that macro and all nested macro calls, and then I just format that, this is what that macro expands to. So I basically took that macro, expanded it, and that got my starting point for main. And the reason I wanted my own starting point for main is I wanted to add some information to that context. And the way to, you can't really do that inside a benchmark function. This is basically name value pairs. And if you try to add the same name twice, it will give you an error, so it just complains. The right way to do it is to do it in your main before you've invoked any benchmarks, so that when the benchmarks run, and the first thing that it does is to report this context information, and that's where this static target line came from in my context output before it began running any of the registered benchmarks. So, like I said, simplest way to get that boilerplate was to invoke the macro and then just have ReSharper expand the macro recursively for me, and then I can go and add my little extra information to the context. Otherwise, we'll take a look at our iterate file here, and it's again really similar to what is shown in the standard documentation. I'm not doing anything fancy by parameterizing my benchmarks. Nothing wrong with, I mean, I probably could, make these benchmarks a little fancier and put some parameters in, but we're just getting at the basics here. This benchmark macro, if we expand that and then reformat the results, you can see that really all it does is it makes up a unique name for a variable. This is that pointer. It initializes that pointer by newing up some state and returning it to you. It returns that pointer so that you can do that dash greater syntax to add arguments and so on. But really, what this is doing is just registering that function with the benchmark system, giving you access to the pointer to the registered state so that you can then call those builder methods to customize the particular benchmark with inputs and so on that parameterize the runs. So for each of my benchmarks here, it's pretty boilerplate in the sense that I am invoking a function that corresponds to this particular case. So really the more interesting part is look at the implementations and see how they differ. So here's my implementation that's using a standard complex class value type from the standard library. This is a standard Mandelbrot set iteration. The formula advances by taking a point in the complex plane, multiplying it by itself, and then adding a constant. We do that for up to however many value that max iter is. In my case, it's set to 64K up here. So it's doing quite a bit of, assuming the point doesn't get a magnitude that exceeds 2. If the magnitude of the z value exceeds 2, then it is mathematically proven that the point is outside the Mandelbrot set, so it can be, there's no point in doing further iterations because it'll be known to be outside and not inside. So standard complex is a template class based on the type of the underlying coordinate value. So standard complex is defined for float and double and long double. On MSVC, double and long double are the same, so there's no point in doing an extra benchmark comparing double and long double. I believe GCC does have a long double type that is more precision than double. I can't remember if it's a 128-bit double or if it is the 80-bit Intel double. But on MSVC, there's no difference between double and long double, so I'm only going to compare float and double. I'm just instantiating that algorithm for complex of float and a complex of double. Here I've got my own homebrew complex class, and I've only implemented just enough to support the code that I've written in these benchmarks in this little example program. I did write tests for my complex class to verify that my implementation was correct. Otherwise, that class doesn't do any error checking. Standard complex as a complex value or complex number value, it has to do a bunch of things about, is one of the arguments a nan, or is it, infinity, or is it negative infinity? It does those checks to ensure correctness and compliance with the constraints of IEEE 754 floating point math. But maybe in my case, I just want the math to happen, and I'm not going to check those edge cases or those error conditions. So I dispense with that with my own complex number type. But otherwise, it's the same algorithm. I'm just using my own complex number type instead of std complex. And then finally, this last variation of the orbit algorithm, I'm not using a complex class at all. I'm using just either float or double intrinsics, and I've expanded out all the math. And then here I did a little math to expand out that when you take a complex number and square it, you can simplify that squaring to one less. I think it results in one less multiply, 3 multiplies instead of 4 in order to compute the square. And there, in the standard library, there's no square function. There's square root, but that's the opposite of squaring. So it's possible that the optimizer and the compiler can recognize that, z times z can be done with one fewer multiply. I don't actually know if there's any attempt to apply that optimization either in the compiler or in the implementation of std complex. In the implementation of my homebrew complex type, I didn't provide a square function or attempt any optimizations in the multiply operator to try and determine if this value the value that's passed in and the this pointer, if they were potentially the same thing. I just did the straightforward multiply. But here, if I'm going to go to the trouble of just operating on the primitive types instead of on the complex number value type, I might as well go through and figure out how to do this with as little work as possible. And you notice I do star equal and plus equal. That's the thing you could benchmark. Is doing the star equal worth it, or is it, and the plus equal, or is it just easy? Is it work out to be exactly the same from the optimizing compiler if you just say, zi equals zi times this plus ci? Who knows? We can know by doing that as a benchmark, looking at the assembly language perhaps on Compiler Explorer. I didn't try that in this particular case because I was more interested in comparing these value types to the homebrew primitive math versus SIMD algorithms, which we'll see in a second. So as I mentioned before, there's no point in trying to make a SIMD algorithm for this iterate algorithm because the data dependency is such that you can't get any parallelism out of a single orbit. However, if we look at the algorithm from computing a span, now here, when we end up calling this code, there is memory allocation going on because we're going to return a vector of iteration counts. If I wanted to eliminate this memory allocation and the memory copying well, the copy will be deleted because we're doing return value optimization here. But if I wanted to eliminate the interaction with the heap and avoid measuring malloc as part of my benchmark, I could have passed in, an output pointer to take the place of this, standard vector, and then I'd just be measuring, what it's like to call the iterate algorithm for each of the pixels. But this kind of makes it a little more interesting for benchmark purposes to include this vector. How bad does that really change things? That you got a memory allocation happening in the middle of each call. It probably, because this is going to get called repeatedly during the benchmarking framework, it's going to be allocating a chunk of memory and then releasing it, and it's the next time it goes to allocate memory is going to be the same size as the one that it just released. So it's probably you're only going to see the overhead for the first iteration, and then it's going to wash out for the others because you're allocating and releasing the same size memory every single time you pass through the benchmark iteration. However, the more interesting part, this is using stud complex for a span. This is using my homebrew complex for a span, and then using just manual arithmetic for a span. That's all, very straightforward. But when we want to use highway to do a span of pixels using SIMD, this code, I basically copied it from the inner loop here, basically copied that from the highway example that we worked up a few months ago. Now we've got the arguments rearranged so that they have a consistent signature with the other algorithms that we're invoking. Otherwise, again, still doing a memory allocation for one span of pixels, but the SIMD algorithm, as it computes a chunk of pixels, is going to write the results into that output vector and then skip to the next chunk of processing for the output vector. Here's my little function that was called to add the static target name to the context. And this works here because this, highway target expands to highway static target, which is always, selected at compile time. So that works just fine. The dynamic version, we have this machinery from highway that gives basically a version of this code compiled for each of the target architectures supported by highway. And then down here in this highway once block is the stuff that is only compiled once. And this is our dispatch table to the different implementations for the different instruction set extensions. We use that dispatch table, pass the arguments to the selected function from the dispatch table, and then otherwise this interior code here is identical to this static instruction set extension. So when we look at our span benchmarking code, you see that there's a call to the static float. I didn't bother to make a static double version. I just did a static float versus dynamic float. And when we run those, this is a release build. It's when you're measuring performance, it's important to use a release build so that you are getting a measurement of the optimizations that the compiler is putting into your code as well as your choice of algorithm. And what's interesting in this result is that for standard complex, the double is faster than the float version. And that's a little surprising because you would think because a float is 4 bytes and a double is 8 bytes, so you would think that it would take more work to do an 8-byte computation than to do a 4-byte computation. But we got about, 1,500 more iterations. It took, 131,000 nanoseconds, so 131 microseconds, versus 185 microseconds, 188 microseconds. So this was faster for some reason. I haven't looked at the assembly code to try to figure out why it was faster, but that was a surprise that I didn't expect. And what's interesting is when we just go to my homebrew complex class, they're basically identical, the float and the double. Again, surprising because you would have expected that maybe the float would be faster, but it wasn't. And then when we get down to this manual arithmetic, now we see that the float version got more iterations. What's interesting here is it's saying it took it's saying it took less CPU time for the double than for the float, although the float got more iterations than the double. Or more iterations of my benchmark loop were executed for the float case. This is the number of CPU nanoseconds per iteration. So that's why it with modern CPUs they're running at gigahertz speed. So that's why the benchmarking library is cranking up the number of iterations of the inner loop in order to get a CPU time that is statistically significant. Over here, this total iters value that's appearing in this user counters column, that's coming from my code. What I'm doing is before I start iterating the benchmark, I've got a counter set to 0. I'm adding up, in the span case, I'm adding up all the iterations that came back in my output array, accumulating them, and providing a total iters counter and storing that value so that it gets reported per benchmark. Obviously, these total iterations are coming from the span benchmarks. Sorry, wrong span. This span down here. So you can see here, it's the same thing. I've got a counter that I set to 0. In this case, I'm just accumulating. Sorry, that's the span. We meant the iterate one. The iterate one. And here the counter is an int. It doesn't. I didn't need as large a dynamic range as for the values as I needed for the span. But I'm just adding the iteration count that came back from that function to the total number of iterations that I computed, and then recording that in the counters for that benchmark case. So you see that's what these values are over here. So 267 million iterations, and for 4,073, this is the number of inner loop iterations I did for my Mandelbrot set orbit computation. This is the number of iterations that the benchmark was executed in order to get these measurements. And you can see there, 265, 267 million, 367 million. And obviously, if these numbers are the same, then these numbers are going to be the same because my algorithm is deterministic. So for the same number of iterations of the inner loop, you're going to get the same number of iterations to determine the orbit of that point in the Mandelbrot set. Now over here, when we start computing numbers for the span, because I'm computing many more pixels, or I'm computing a number of pixels per execution of the benchmark loop, that's why the iterations of the benchmark is only 34. The number of orbits, or number of iterations computed for all the orbits for those pixels is comparable, 254 versus 267. And then when you really see things change is down here is when we start to use the SIMD algorithm. So now with the SIMD algorithm, we're getting parallelism in the CPU, even though we're using only a single thread. And you can see that because the span loop took less time, or to compute a span took less time, we were able to get more iterations of computing a span of iteration counts using SIMD, and we got up to 1.4 um, giga iterations, I guess you could say, 1.4 gig. And then with the dynamic dispatch that chose a more favorable, more performant SIMD extension set for my CPU, we got almost 2.8, 2.78 giga iterations. So, not that I'm an expert in performance analysis, as I said, but what we saw here is we got a surprise. Why was double faster than float for std complex? I don't know. I haven't looked at the assembly code that was emitted. I mean, obviously, if we go look at the assembly code that's emitted, we could probably figure out why. It could be that in the MSVC standard library, it could be that std complex of double has had more optimization applied to it. It could be that when using doubles, the compiler might recognize might spend more time trying to find more optimization opportunities. It might emit some SIMD vector code in order to get a little bit more performance. It's unclear. You can see from my source code that the algorithms that I wrote are the same. The only thing that's different is the template parameter to std complex. Now, std complex can be specialized for float versus double, and maybe there's something in there in that specialization that made double perform faster than float, but that was counterintuitive. We expected, as in our manual case, where we did manual arithmetic, we expected that float should be a little more performant because you could fit, because the float is half the size of a double, right? So you usually think space-time trade-off. So if there's more work to be done on more bytes in order to compute the value, you would expect that the float case would get more iterations done in the same time or take less time for a single iteration. And that was the case for my manual math expansion, but it wasn't the case for my, they were identical for my, there's a slightly different wall clock time between my manual complex float class, my manual complex double class. Maybe we can just go double check that to make sure. If we go look at span and we look at span complex float, you can see here I'm invoking the overload with float arguments. If I drill into that with F12, we're in the float version, and I'm constructing a ComplexT of float before calling this algorithm, and this is all parameterized on the template type, so I'm not going in, the measurements were the same, but I was going into different code. This is a ComplexT of double, and that otherwise it just comes down into the same template algorithm. So I didn't mess up my code, but for some reason, the double and the float versions of my homebrew complex type ended up being the same. And then we kind of got our intuition confirmed, thinking floats should be faster than double when we did the manual math. But these are small changes compared to the big boost of using SIMD. And this is an example of, you can do these micro optimizations like I did with the manual math here. And if I didn't have SIMD extensions on my CPU, that's worth, eschewing these abstracted value types of a complex number and doing the mathematics, kind of inline for a complex number, we did take advantage of the fact that we could get one fewer multiply with a z-squared. But you notice that even though we did that, for the double, it was the same as using our own homebrew complex type, and it was the same as using our own, or using the stud complex from the standard library. Whereas the big win is using SIMD. So here, obviously, if I wanted to make my Mandelbrot set computation go faster, the obvious first thing to do is to use SIMD. After I've done SIMD, maybe we look at, not using the SIMD code does not use stud complex because the SIMD registers, they hold floats or doubles. They don't hold complex numbers intrinsically. So the SIMD registers don't know how to do complex math. We have to do that ourselves. And it also implies that maybe there's some error checking and some edge condition thing, how nans are handled, or how infinite numbers are handled, or negative infinite numbers. The SIMD instruction set documentation describes how they handle those edge conditions for each of the operations, but those edge conditions are not necessarily compliant with the rules of IEEE floating point arithmetic. So there may be, and furthermore, they don't necessarily comply with whatever the standard says about the behavior of stud complex. So this is equivalent to using my own homebrew manual math. I'm essentially doing that by just dropping down to the operation of floats. I'm not using a complex number value type, and I'm not using stud complex in particular. So, however, that's where the big performance gain is going to come. And I think that's the most important high-level takeaway you can get from writing benchmarks is to compare algorithms. Now, I didn't even use, if we go look at my iterate implementation over here, just make sure we're in the right file. This, yeah, sure, this is the simplistic version of the inner loop of a Mandelbrot set orbit computation. However, when you actually look at the number of iterations computed for these particular points, if we go back to my benchmarking code, I'm asking for the orbit at negative 0.75, so negative 3/4 on the real axis, and 0 on the y-axis. Now, this is a point that's the boundary of what's called the main cardioid in the Mandelbrot set. It's inside the Mandelbrot set, and unless I do something fancier in my orbit calculation, we're basically going to run to the maximum iteration count on that point. And if you run this code in the debugger and look at the iteration counts that are returned, that's what's happening. Is for every time we compute an orbit, we're running that orbit all the way out to the maximum, which is kind of what I want for this benchmarking, this fractal computation, because I don't want it to bail out really quick. That doesn't tell me much about the inner loop because the inner loop wasn't executed very much. However, when you are computing the orbit for a point inside the Mandelbrot set, one of the things that tends to happen for many points is they hit what's called a periodic attractor. And what that means is that the sequence of new complex numbers that are computed for the orbit falls into a cycle. So if you add period checking, so you did an enhancement to this basic algorithm, this is the simplest algorithm you can have for computing the orbit of a point in the Mandelbrot set. If you enhance this to include period checking, then you probably won't reach maximum iteration count on that particular location of -3/4, 0. We'll probably determine that it hits a cycle and we just exit early because, there's no point. When you're in a cycle, it's going to continue to compute points in the cycle forever. So you'll never escape the Mandelbrot set. So therefore, once you've determined that a cycle has been detected, within some tolerance, obviously, because this is computers here, it's not infinite precision math. Once a cycle has been detected, you can bail out early as soon as the cycle has been detected. So that's one obvious thing that you could do. Another thing that you could do to improve the performance of these algorithms, especially when the iteration count is set very high, like I've got it set to 64K. In the old DOS days, you would set this to like 128 or something, because you didn't want to wait forever for your very slow CPU to compute these orbit calculations. So that's one of the reasons here why you see this total iteration count, is so high for a certain number of iterations of that loop, and that's because I intentionally chose a point that was going to require many brute force calculations up to maximum iteration count before that loop would terminate, my innermost loop. And there's other algorithmic improvements that you can make as well. And so it's not just mapping your algorithm most efficiently to the hardware that you have available, which is what SIMD does, compared to a single floating point value register. That's obviously a good starting point, but also algorithmic enhancements are usually the best way to improve the performance of your code. So don't just think in the micro, even though this is a quote-unquote micro-benchmarking framework, don't just think about the emitted assembly language when you're trying to get the best performance from your code. Think about, asymptotic complexity of the algorithm that you're using. Think about, and cache. You will be able to use this library to, identify times when you're basically just blowing out the data cache. And in my case, these algorithms, they're all CPU bound. They're not IO bound. So they're not bound on, there is some vector copying going on here, but that's not what's happening for the majority of the time here. Majority of the time here, we're looking at an algorithm that I've intentionally coded it in a way that it's CPU bound. It's not getting a lot of cache misses and so on. However, you can use the benchmarking framework. If you just go back over here, you can use this library. Let's go back to the user guide. You can use this library for testing the effects of cache and data organization and how that results in different performance. And one of the interesting things, that's not the one that I want. So when you get into that level of measuring performance, you can end up bumping up against the compiler. The compiler may optimize out. Here, preventing optimization. That's what we want to look at. The compiler may do something where it took something out of the inner loop of your benchmarking loop and, determined like, I can take this and just move it outside the loop and, that'll be faster. And while that's true, it defeats the point of what you're trying to measure. So the library provides this function, do not optimize, and that takes some expression and it marks the result of this expression as a thing that is not to be optimized away. Now you might say like, well, how is this going to be optimized away? Well, the answer is because X is initialized and then X is modified, but X isn't used outside of the scope where it is declared and modified. So the compiler might be smart enough to look at this whole thing and say, oh, well, you initialize X here, you modify it here, but then you don't ever use the value, So we can drop X altogether. And then once we do that, we just have like a bare use of I. And then that doesn't have any side effects. So we can drop that I out, which means we can drop this whole loop out, which means we could drop the entire contents of your benchmark out. Doesn't a good optimizer can look at that and say, let's just get rid of the whole thing. You're not doing anything of consequence. But your point was you wanted to try and measure this. How long does it take to increment this variable x with the value I? So by putting this, wrapping it up in this benchmark do not optimize, it ends up telling the compiler, you may be really smart and you may be optimizing all of this away, but just don't be that smart. Do not do that. It does that through some various trickery, usually involving, declaring things as a volatile pointer or maybe some piece of omitted assembly. The specifics are not that important, but that do not optimize, if you find like your benchmark is going ridiculously fast, it could be because the whole thing got optimized away. So you may need to result to this do not optimize call. There's another function here that's provided called clobber memory. And the point of that is to make sure that side effects that are supposed to happen in memory actually take place. So again, in this case, we've got this vector, but its scope is such that, we pushed back onto it and then we exited the loop, which meant the vector got destroyed. So, maybe this reserve and this, use of the vector, maybe the whole thing got optimized out. What they did here was they said, don't optimize the data pointer, so the pointer to the data held by the vector, that keeps that pointer alive. And then we modified the vector with pushback. And then we, with this clobber memory, it forces the value that we pushed onto the vector to be, observable outside by the fact that it wrote to memory. If somebody else had a pointer to that memory, it works out in such a way that the compiler will do less optimizations because of this call to clobber memory. So it will keep this code alive as written so that you can measure what it's actually doing instead of measuring the result of the compiler optimizing it away. Now, it gets tricky. This stuff is obviously specific to the compiler optimizer behavior. If you get really unsure what exactly is executing in your benchmark, you can always just look at the assembly and see, are the loads and stores that I expect to see happening, are they happening? Are the calls to the memory allocator that I expect to see happening, are those happening, etc. So that's an important thing to mention in terms of algorithms that get, I'm measuring relatively coarse operations by calling these functions that do many iterations. It's unlikely that the optimizer is going to interfere with what I'm trying to measure because it's, hundreds of CPU instructions, not one or two. But it is a microbenchmarking framework, and sometimes you do want to measure those very small effects to understand what's happening. So you may need to interact with the compiler in that way. Okay, so the rest of this stuff is really straightforward. If you want to understand in deeper detail the effects of that do not optimize and clobber memory behavior from the library, there's a good talk by Chandler Caruth about microbenchmarking from a few years back at CPPCon. He goes into a lot of detail showing assembly language and so on, what's happening there. And he's a good presenter and very clear in his explanations, so I didn't feel the need to repeat all of that. I just wanted to show you my results at comparing a bunch of different implementations for the same algorithm to see what I could learn about how I could make things go faster. Now, ultimately, I'm going to try and use this microbenchmarking library on one of my open source projects where the inner loop of computing the orbit, it's got periodicity checking and all kinds of other things going on. There's a lot of conditionals in that loop. I have a feeling that, maybe applying some template extraction to that and using compile time, code selection, kind of if const expert kind of thing for getting different variations of the same algorithm, that might yield a faster inner loop on my code. But that's a big thought experiment. But this library would let me try that out to find out if that's even worth it. It could be a whole lot of effort restructuring that code just to find out that it didn't make any significant difference. And now that code is not SIMD enabled, so this tells me the very first thing I should try to do is to try to make that code SIMD enabled. And you might ask yourself, like, well, fractals are ridiculously parallel, so why don't you try multi-threaded before you go SIMD? And if I were writing this code from scratch, that's probably what I would do. But in this case, the code as it is communicates through a lot of global variables, and that means multi-threading introduces a whole level of other bugs and synchronization, concerns that you have to go through in order to get things communicating correctly through global variables. So I actually think SIMD is a bigger perf boost within reach than multi-threading. Eventually, of course, I do want to get multi-threading because multiple threads with SIMD would be another multiplier. But SIMD feels like a multiplier that is closer in terms of code changes and risk than going multi-threaded. So this code will be up on GitHub, and enjoy your benchmarking, and that's all we have for this month.